Okay, welcome back. Now I will continue to show you some engineering examples that the engineers need to solve a second order ordinary differential equations. Usually some applications in mechanical engineering, if you have a washing machine, if you want to design a washing machine, this is the outer part of the machine. A steel box, and this is the drum. The drum is hanged by two spring usually, and there is two viscous dampers at the bottom. Okay, so when the machine rotates with its maximum angular velocity, usually the engine of the machine has an angular velocity of 1000 revolution per minute, or RPM. The closed capacity of the machine due to the eccentric mass when it rotates, this is the mass of the cloth. It is usually about 10 kilogram, for example, or 7 kilogram, depends on the design. And you want to reduce the lateral and vertical vibration. You don't need to have a lot of noise. So the engineer need to find what is the suitable stiffness for this spring and what is the suitable damping constant for this damper. So again, it is as I tell you before in the previous video, you have engineering system, you have input, and you have the response. So my response is the lateral or vertical vibration is y, my y here. So if you write the second equation of motion, this is what gives you, due to eccentric mass, there is a vertical and horizontal forces, and this depends on the angular velocity, omega. I will tell this omega, angular frequency, and this will be m total times y double prime plus c y prime, y is my lateral vibration, plus k, the stiffness, times y, times here you will have a sinusoidal sine omega t with some amplitude. So this is a sinusoidal excitation force acting on your system, and if you want to minimize the lateral or vertical vibration, which is your y function, you have to choose the suitable k for the spring constant, suitable damper, and also the total mass is the mass of the cloth. I will call it mc, and the plus another additional mass md, or additional mass. Usually they put some over the drum here, some stone part to increase the total mass and reduce that vibration. So all of these will affect your response. Again, the omega, or the angular frequency of the engine, is also important. If you have a very low, for example 500 RPM engine, rotate with this speed 500, you will find that your vibration is too high and it is too noisy, maybe 10 centimeter or more. But if you increase the angular frequency of the engine, of the exciting force, to, for example, 1000 or 1200, or you will have RPM, of course, you will have a less vibration. We will speak about this in the next videos about this application. So this is in mechanical engineering. Also in mechanical engineering, you have another example for second order ordinary differential equations. You sometimes need to design the suspension system of a car. If you have a car, this, and you need this, the body of the car is a suspension on the wheels, of course. This is you need to have a spring here, and also a damper that connect the wheel to the car, and if you have a bad road, okay, it is a not good road, and this road will cause excitation on my system, you can model this as a one mass of the car, and this is the spring, and this is the damper as well, and there is this is the wheel, and this is going on the road. So you have again here a sinusoidal excitation, and you have m y double prime plus c y plus k y. Y is the vertical excitation or vertical response, and the engineers needs to have a comfort to the people in this, and this should be minimum, so they have to design their k value or c value accordingly. Okay. All what I speak in these videos, I speak about what we call initial value problems. Okay, so problems that depends on time, response depends on time. But sometimes in some problems you have what we call boundary value problems. Boundary value problems. Sometimes you need to solve these problems. For example, if you have if you need to design, a factory building, you need to use, for example, a steel truss for the roof system, and long columns, maybe 10 meter long. Okay, of course this repeats itself. This is the factory. So these columns, because they are long and cylinder, it may have what we call a buckling problem or instability problem. So before it got material failure, this column may have what we call lateral buckling under the effect of loads. Okay. So also some of these members here will have some tension, and for example this has some compression. So some of these members also has compression forces, and the engineers need to check the stability of these thin members and against what we call the buckling loads, and they need to find buckling, critical buckling load. So in this case, I will speak actually in details later. This is a boundary value problem. It depends on the connection details here and here. Okay, so if it is just pin connection, so the buckling load will be like that, and if it is a fixed pin connection, it is maybe like this. Okay, so there is no rotation in this. So this is the lateral buckling. So this is my y, and my y is function of x in this case. If I call this axis a x-axis, and I call this axis as a y-axis, so my function is my y, my response is function of x, a function of the position. So we call this boundary value problems. These boundary value problems also you can write the second order differential equations to find what is the maximum critical load that may cause for you a buckling. Okay. Okay, so as before we say this is the general case of the second order ordinary equation. I have an action acting on your system, I call it Q of T, and this is your engineering system. It may be a washing machine, it may be a multi-story house, it may be a suspension system for the car, it may be a buckling problem, and you have the response function which I call y, and these are your design parameters. If you're not happy with the response, you may change A, B, C values, and you look for a better response. Okay. Sometimes we call these types of equation non-homogeneous equation. Non-homogeneous non-homogeneous equations. Okay? If the action is equal to 0, so sometimes you had here the action force that acts on your system is 0, but you still have a response, you still have a motion. Okay? We call these types of equation homogeneous equations. How you can find the response and if you don't have an action force? Actually, you should have what we call initial condition. Initial condition. So in the beginning, suppose that you have this is your building and you want to find the response of this building. Okay? So usually you give it an initial condition, you give it an initial condition. For example, you give it a pulse force, you give it a pulse force, or you just pull it with a crane. Suppose that, imagine that you hang it from this point and you pull it with a crane, and then you suddenly cut or release this. So you give it initial displacement. Y0 is, for example, 10 centimeter or 5 centimeter. Okay, it's 5 centimeter. Okay, you give it initial displacement, then you release, and this need to have a vibrate. Okay, so depends on this initial condition, you will have a response. Also, you may get some velocity or some pulse, means y prime 0 is that much, you get some value. So giving an initial condition, you still have to find a response. We call these types of equations homogeneous equations. Okay? Okay, so these types of equations, the response of the homogeneous equations. So in this course, I will explain how to solve these types of differential equation. Because you don't have an action function, the response or the solution for this homogeneous second order differential equations depends on the characteristic of the system. It means that depends, if you have a vibration problems, depends on the mass of the house, depends on the damping characteristic of the material, depends on the stiffness or the strength of the columns and beams, and etc. Okay, it's in case of course, this is speaking about a dynamic response of the house. Okay, so it depends on this characteristic of the system. Okay, so that's why these type, and of course depends on the initial condition, how much you apply initial condition to the system when the time was equal to 0. Okay, so or depends on the boundary condition in case of boundary value problem. So that's why these are the characteristic of the system. To solve these types of equations, we need to write what we call a characteristic equation of the system. You just write it like this. You just put these coefficients as same, A, B, and C. This is not a change. Suppose that you select some numbers here, okay? And instead of y double prime, I will write the new variable lambda square. And because I have here a derivative for the 2, I write a quadratic equation. I will change this equation to what we call a quadratic equation. So instead of the derivatives y double prime, I write the lambda square. And instead of the y prime, lambda to the power 1. Okay? And instead of the y, I write lambda to the power 0. Of course, as you know, lambda to the power 0 is equal to 1. So you don't need to that. This is equal to 0. So I change my differential equation to a quadratic equation in lambda. It's a quadratic equation with the coefficients A, B, and C. We call this is the characteristic equation of the system because if you change these characteristics, the solution will change. Because this is a quadratic equation, you will find the roots, lambda 1, lambda 2, it has 2 roots, and depending on these roots, the solution for a homogeneous ordinary differential equation. It may be a exponential function to the lambda 1, for example, t, or it may be a sinusoidal function, or it may be both sinusoidal and exponential function like this. Okay, so this is the peak. If you connect the peak here, the decay, okay. So this is the exponential function multiplied by a sinusoidal function. So next video, I will speak in details how to solve these types of equations in the next video. Thank you for watching.